So the today topic is acoustic tomography. And before starting, let me share you with some images taken this last weekend. We had unusual snowfall, 30 centimeter snow was falling, and some trees damaged due to the heavy snow load. And now the temperature is increased, so snow is melting. But for a few days, we had wonderful winter images in the city. So the title of this presentation we will present together with my son György is Advanced Acoustic Tomography, and we will focus for the biomechanical evaluation mostly. Just to get there, I need to introduce the technique shortly. For those who participated in the presentation last year, they will see some images is well known by them, but I apologize for that. But as an introduction to the technology, I believe it is important. But the major part of the presentation is brand new, dealing with biomechanics. So our company business form has changed last year. Now we are working as a limited company, and also the ownership changed. My sons take over the company. So these are the background, but not really related to the topics. And our goal, our company mission is keeping urban trees as long as possible while maintaining the safety. So we will focus in the speech about the biomechanical evaluation, safety factor calculation, how the tree height, the crown area, tilt angle, the selected tree species, wind speed, wind model is influencing the result, and how to interpret it. Before starting, just few image is highlighting how the topic is important. These images were taken in Hungary in the past few years. Time to time, after storms or heavy snow load, this type of failure may happen. As you know, the evaluation of trees always starts with visual. So visual first. The result of the visual tree assessment gives us the information about whether instrumental urban tree assessment is necessary or not. Most of the time, only the visual assessment is enough, but not all the time. If necessary, what type of instrument is necessary, and what are the critical layers of the tree we need to investigate. This is a well-known image by Klaus Matek and the colleagues. The visual tree assessment explain you the visual indicator of possible defect in the tree trunk and heavy branches. As you know, just a few of them is fungus fruiting body on the trunk, holes, birds' holes, another fruiting body, wound. There is a very simple technique, the rubber mallet, sounding the tree. Experienced users give information about the internal condition. I mean, advanced, big, hollow, or decay may found by these simple techniques. Needs little practice, but has some limitation, of course. And let's see how we started almost 32 years ago with the single pass acoustic technique. We call the instrument microsecond timer. It measures the transit time between two sensors. And whenever there is a feature in between the two sensors, like a hollow or decay, the transit time is remarkable increasing. In this slide, you see a green line where the sound is propagating. Of course, sound is not propagating straight line, but rather three-dimensional. This is a historical image we showed at the first European Wood Entity Symposium, our instrument, the Fakopp microsecond timer. It was 1994. And Károly Mészáros, my former colleague at the University of Sopron, is using the instrument. Actually, he was recommended using the acoustic technique for trees because earlier it was used mainly for the evaluation of wooden structures. And that trial was successful. So near City Győr, he is testing one of his first three. And I like this little movie. You see how the sound's propagating in two-dimensional frame. Whenever there is a hollow or decay inside, the sound waves arise later. It is just a clear indication that the physical background, the technical background of the model is solid. So this is working all the time. Two sensors for a single pass and a caliper because the instrument measures only the time and we need to know the distance to calculate the velocity, and the relative velocity change indicates the problem inside. Higher the relative velocity change, higher the defect inside. Some defect we found by this simple technique. And now let's move to acoustic tomography. Three-dimensional realization. When we use more sensors, more paths, we are able to map the internal condition of the trunk. Here you see the velocities are around 1000 meters per second, and those lines crossing the hollow is dropping down to 600, even 400 meters per second, indicating clearly that that area there is a defect. Using advanced maths, we are able to reconstruct the internal condition. And here you see beech tree log, decay, and the photo together. This is the system with 32 sensors. We just checked what are the differences when we are using 10 or 32 sensors. You see the contrast and the the geometry recognition is much better when we are using more sensors. Generally, more sensors, better resolution, but longer time in testing procedure, and of course higher prices. Most of the arborists are using 12 sensors or 16. The measurement is quite quick. Experienced user can produce a result within 3 to 15 minutes. And I don't want to show the video. We had a competition on who is the quickest in acoustic tomography measurement, and the winning team was with a time with 2 minutes and 21 seconds. 2 persons, easy geometry, breast height, so easy access. But the daily practice of the Fakopp company, this is a company who is taking care of trees in Budapest. They have a cycling time of half hour, 30 minutes, including going to the tree, performing the test, and preparing the final report. Well, whenever the cross-section is irregular, we need to use triangulation technique, and this is our digital caliper, help us to perform quick recognition of irregular geometry. Whenever we perform not only one, but 2 or more layers, it is a possibility to build up a three-dimensional image. Here you see another one. And also the vertical image is together with a photo indicating that this tree has severe decay at ground level. The biomechanical evaluation. So now I touch the heart of the presentation. Unfortunately, not all the ArborSonic users are performing the biomechanical evaluation. And for this reason, we are focusing to this direction because I would like to explain you that it is quite important. When I go back, here you see nice color images, but these are only color images, and the interpretation of these images are not always easy. That's why we need the biomechanical evaluation. Why is important the biomechanical evaluation? The presence of the internal decay is a useful information, but only part of the total story. The tree safety is influenced by many other parameters like tree height, crown center height, tilt angle, tilt direction, crown area, trunk diameter, wind speed, tree species. So we need to take all this information into one basket and get the final result. What is safety factor? Safety factor gives you one single number, and this number characterizes the safety of the tree trunk against rupture. The definition of the safety factor is the strength of the wood material of the selected tree species divided by the total stress, compression stress made by the wind, the self-load, and whenever the tree is tilt, the self-weight is creating another torque, another bending moment. The first step of the evaluation is the simplification of the color image. Because the color image is too complex, and the simplification is done at the yellow border. You see where you see the yellow colors, we cut the image. The blue indicating intact material, this blue on the middle image indicating the intact material, and the white where is no color indicating that part is not supporting the tree stability. It can be decay, hole, or even a deep crack. And also you see a red curve here. The red curve indicates the mechanical stress depending on wind direction, and the distance from the center of the image is indicating the amount of the mechanical stress. And the line is shown here is indicating the wind direction causing the highest stress. So this is a critical wind direction. If you recognize the remain intact shape, it is really visible that this direction is critical because the remaining wall thickness is much less than perpendicular. Okay, so this is first step. From the color image, we simplify. Then we calculate the second moment of inertia. This is coming from the mechanics and maths. The definition is a double integral. I don't want to go deep, but we are using this formula. This is well known in principle of mechanics. Then we calculate the stress made by bending. The bending stress is a combined stress, has compression and tension side in the center line is 0, but in this expression we can calculate the highest bending stress. M is the bending moment. This is length of the arm multiplied by the acting force. We measure in Newton meter, and the perpendicular distance from the neutral axis is the epsilon, and I showed you earlier the moment of inertia. So the safety factor is then calculated using the ArborSonic software, and this part of the software will present by György with a live presentation. Please, György, continue.
Welcome, everybody. I'm very happy so many of you have shown up for today's lecture. I'm going to do a small demonstration for those who haven't used biomechanics so far in the software live. So I'm not using slides. This is going to be the ArborSonic software right here. So we are assuming that we start from a measurement we have already completed, and we have time data at this point, and also a pretty nice measurement. I want to take a look at the tomogram first. There is a small amount of decay or hollowness in the tree trunk, and now we are ready to accomplish the biomechanical evaluation. So in essence, before starting, we support two different models. One model is the EN 1991, which is a Eurocode standard, and the other one is a uniform model. These models operate on different principles because the EN model operates from a basic wind velocity that is defined for every country. Parents is going to show this, and also the data source from which you can enter the base wind velocity that is defined by the standard and also the national annexes. And it's different for every country depending on the location. It is very different, however, from the uniform model. The uniform model uses the drag equation known from physics and also assumes a uniform wind speed for the whole area of the tree. First, I will show you the EN model. We are selecting a terrain that these settings essentially have different kinds of multipliers for the base wind velocity. For example, if you select seashore, that will result in a much higher wind force later on. All right. In the crown model, we can select the drone or calculator. The main method that we do now is the drone method, and I will show you that. First of all, you need to go to the image container and import a new image. That can be done with this button. I have already done it here. And then you can close the image container with this upwards button. So the first thing that we do is draw the crown area. I have to stress that you have to take the image from far enough to avoid perspective distortion. So sometimes people take a picture from just below the tree, and that's not great. We need to get far from the tree and create an image from there. Okay, after clicking this button for drawing the crown area, I can put down points that are going to show where the outline of the crown is. Now, this is a difficult image because several trees are overlapping here, but I will try to follow the crown. You can see that sometimes there are small branches that I do not include. You have to think about, are they load bearing? And you can easily see that those small leaves are not really load bearing. It is not comparable to the state of the center of the tree. So it's perfectly fine if there is a little leaf that is not included. Unfortunately, the image doesn't include these branches, so I will do my best here. And also at this region, there is a tree behind that I'm going to skip. Now I'm finished with drawing the crown. Okay, after this, you have several buttons on the right, which you can use to edit the crown, to remove or add further points. The fourth button is the reference. This tree is 21 meters. So what I need to do is put a point down at the base of the trunk and at the top of the tree. And then after clicking these three question marks, I can enter the height of the tree, that is 21 meters here. I would recommend that you do not use small objects. So do not mark something as like a car or a person, because you want to avoid the kind of perspective distortion that would result in. What you want is mark the whole tree with the total height. That is the best method. Okay, and the last thing that we need to do is to mark the ground and the direction of the lean. This can be done with this yellow button. This is the fifth button on the right. First, I need to mark the base of the tree and then a horizontal. Now this image is, you can see it is a bit tilted, so the horizontal should be following that tilt, not much. And then I take a second point, and very often people confuse the second point. It's not the direction of the trunk. It should go to the direction of the center of mass of the crown. So in our case, the center of mass is a bit to the right on this tree, and I will put a point there. After clicking OK, we already get a safety factor, and just as a quick explanation, the drawing also calculates the area, crown area, the top height of the tree, the bottom height of the tree, and the center height of the tree. We have the tilt angle, which you can override. So now draw tilt angle means that the tilt angle is used from the drawing itself. However, you can redefine this. Imagine the case when the tree tilts towards the camera or tilts away from the camera. In those cases, you might need to redefine the tilt angle. And the way to do it is unchecking the draw tilt angle and changing this value. As you can see, as I enter a larger degree of lean, the safety factor goes down. Ferenc is going to show you lots of different experiments and explain how the biomechanics work in detail. We can also set the direction of the lean, and this is very important. Whenever you use the biomechanics, make sure that your direction of north is correctly entered in the sensor geometry. Now, one thing that people use as a rule is to put sensor 1 to north, and then you never have to worry about this again. However, if your sensor 1 is not at north, you can go to the right in the sensor geometry panel, and if you hover your cursor to the north point, you can rotate your cross section and essentially set a different sensor to the north. So as an example, imagine that sensor 7 is going to north. So now I have to rotate this 180 degrees. And now sensor 7 is at north. But always make sure that your north position is correct. The easiest way to do it is to just put sensor 1 to the north. Then you don't have to change it later. Okay, now I will go back to the biomechanics. You can change, I wanted to show the effect of changing the terrain. If I change to a seashore, the model will calculate with larger winds. The EN standard defines different slices for different heights, and each slice will get the wind speed from the top of the slice. There are several things in the standard that is trying to overestimate the wind load. It is essentially made for buildings, but over time, since it's a widely used standard, it got used for tree evaluation as well. I will go now back to village, and for a short while, I will show you how to do the uniform model. So now I have changed to the uniform model. There is a slight change in the safety factor because these models calculate with different assumptions. The EN standard uses the base wind velocity that is defined by the national axis, and it's for a territory. But the uniform model is just using the drag equation from physics and uses the maximum wind speed for which we calculate the wind force. And for this reason, you see a much higher wind velocity. Very often I see the mistake made by users that they use the wind velocity, the highest wind velocity, for the Eurocode model. That is a serious mistake, and you should always consult your national axis and the base wind velocity defined for your area. Ferenc is going to show you this later. It is also possible to change to a calculator method. In the calculator method, you can essentially enter the properties of the crown. In the calculator method, the drawing is not used. You can click on the calculator and enter an area for the crown. And you have different methods of estimating the shape of the crown. Now I have a crown shape that is somewhat similar to what we have drawn here. And therefore we are getting a similar safety factor. I can also edit the degree of lean and also the direction of the lean. And with that, I think I will conclude the demonstration of the biomechanics and hand it back to Ferenc. Give me a second.
So thank you, Jerry. I believe you realize that using biomechanical section of the software is not too complicated. We need to go through this procedure you already seen. Now I did a little play with it. I would like to give you some demonstration of the biomechanical evaluation sensitive to parameters shown here: the tree height, decay area, tilt angle, tilt direction, crown area, tree species, wind speed. Going back a little bit about the two wind model biomechanical section is able to perform. One is the Euronorm. This is valid not only in the European Union, but it is widely used all over in Europe, including UK, Norway, Switzerland, Ukraine, maybe Russia, but I'm not quite sure, but also applied and accepted in Israel and also valid in Japan, but not accepted in China and in the United States. What are the differences? Both methods, the US and the European method, is based on the basic wind velocity. The basic wind velocity is measured at 10-meter height, an open field, undisturbed wind condition, and the Europeans are using the average wind speed over 10 minutes. So it's a very long averaging time. And the US is using the same 10-meter height, averaging for not 10 minutes, only 3 seconds. So the US methodology is based on the wind gust. The European is based on the average wind speed. And from this point, the formulas and everything is completely different. But we have these options because we have users almost all over the world, around 35, 40 countries. Some countries, Euronorm is available, some others not. Those countries where Euronorm is available, I highly recommend to use that model. In the European Union, it is not recommended, it is compulsory. So, the effect of the lengths and the crown height ratio. Time to time, we got a recommendation from users, and they're always very happy to check what are the needs of the users. And this way, we are able to develop our software, becoming more user-friendly and providing more useful information. One of the requests was to introduce this ratio. This is quite simple. If you measure the tree height and the crown dimension and the ratio of these two, whenever the tree is too high relative to the crown, it is less safe. And this parameter is give us information. But be sure this is already incorporated in the system. What I did, on the left, you see umbrella pine and with a short trunk, and the safety factor is just about 150. This is above 150%, we believe that the related risk of fracture risk is low. If I artificially increase the trunk, you see below the image, the yellow line is continuing in the middle. So the safety factor goes down to 100% with moderate risk. And if it's even taller, safety factor goes down to 50, very dangerous tree. And if you compare all the other parameters, I mean, wind and the tilt and all the parameters were unchanged, only the tree height was modified. What you see, this is clearly indicating whenever the length to crown ratio is lower, the safety factor is lower as well. You see the all the three images. The reference height in this special case was only the crown height. It was 10 meters for all the cases. Only the trunk length was modified, and for this reason, the crown area is identical as well. So that's why I only changed the trunk length of this model. This is a little game with the biomechanics, indicating that this parameter is incorporated. Let's see another trial. Effect of decay area. Whenever we started the ArborSonic more than 20 years ago in Hungary, users seen a red spot in the center or even blue, decay, hollow, and they decided to cut. Unfortunately, several tree was wasted on this way, but as you see, the safety factor can be relatively high. Even we have 20% of the total cross section is infected or it's had a hollow. The safety factor is a little bit dropping. You see, when would be no decay, the safety factor is above 150, and in case of 20 is just at the border 152. Whenever the size of the decay is increasing, as you see when going to the right, the size of the decay is from 20 increased to 45, and the safety factor is dropping. So yes, decay is important information, and the biomechanics is reflecting. Small decay has small impact on the safety. Large decay has large impact. Another parameter, the tilt angle. A little bit funny, but the tilt angle we measure relative to the horizontal. Whenever this trunk tilt angle to horizontal is 90, it means the tree is standing straight. Whenever the tilt is increasing, I mean this number is decreasing, the safety is going down, as we expect. Here you see the numbers of different leaning angle. In the software, we have a possibility to select the manual entry of the leaning angle, because the image not always reflecting the leaning angle. Whenever the tree is leaning to the direction of the photo machine, in that case, there is no visual indication. That's why we need to override by manual entry. I did only just change these manual entries, and you see the clear image that the biomechanics is reflecting to the influence of tilt angle. So if I go back to the decay images, in here we can measure. There is a software feature to measure the intact wall thickness, and the very simple parameter, the residual wall thickness relative to the radius of the tree, is a indicator of the risk. Yes, it is, but many other parameters are also influencing. That's why I don't want it to absolutely highlight the intact wall thickness importance, because it is incorporated in the biomechanics. Let's see another parameter like the tilt direction. So last week we tested wall chestnut tree south of Hungary just before this snowstorm arrived, and you see that the tree is leaning and suffer a big decay. There was an opening visually we were able to see, and the acoustic tomography is reflected well to the feature we've seen visually. And the leaning angle relative to the vertical was 15 degree, or in our scale relative to the horizontal is 75 degree, is unchanged. We only changed the orientation. In case of west orientation, the safety factor is 229%, or the safety factor is 2.29. But when the same tree would lean to south, in that case, the safety factor is much higher, because the trunk shape is very, very complicated. In case of circular and intact shape, this feature cannot be seen, but in this case, the leaning direction is becoming important, quite important. So that's why when you do the investigation, this information is quite important to record. Effect of the crown area. This is quite how I did. Yes, just I want to remember how I did. Again, all the parameters are unchanged, only the crown area is reduced. In the middle, you see the already known umbrella pine, and on the left, I artificially enlarge the crown. Its crown is not so big, but the software is taking much bigger area marked by the red curve. The crown area is above 200 square meter, in the middle 160, and on the right I reduced less than 100 square meter. And of course I did much more drawings, and on the bottom you see how the safety factor is influenced by the crown area. The function fits to the inverse of the crown area, and it is fits by the Excel, and the function we found, the X is the crown area, the horizontal parameter, and the power is minus 0.9. Theoretically, it would be -1, but as you know, many other parameters are influencing it. I mean, the self weight of the tree. So that's why it is just indicating that the estimated function is followed quite well. So the effect of the crown area is 100% is incorporated in the biomechanics. This is really, really good to see. It gives us the practitioner gives us the possibility to modify the crown area whenever the safety factor is low. Let's see on the left. This is another image I taken last weekend. The safety factor is around 108%. it's indicating that we have moderate risk. It is highly recommended to do some action. Very typical action in this case, the Cron reduction. And we are using in this model the Euro norm, where the wind speed depends on height. And let's see, the goal was to achieve safety factor above 150 and reducing the Cron at the top. So the red line is moved down, and we lost, the Cron area loss is 45 square meter, and we were able to get the requested safety of the tree. Of course, sometimes it's more easy to reduce the Cron from the bottom, but this is not a realistic image. But if we would do that, we can achieve the same result, safety factor about 150%, but the Cron loss, the Cron reduction is much higher because the wind speed at lower level is lower and the effect of Cron reduction is not so effective. In this case, we lost 142 square meter. So this is a recommendation that always, if you need to reduce the Cron, it is recommended to reduce at the top. It's much more effective. Tree species. There is no visual images, only numbers. Here you see a number of species, and the safety factor by changing the species is changing dramatically. In case of Quercus robur, this is very strong wood material. Safety factor is high, but if this tree would be Aesculus hippocastanum, horse chestnut, in that case, safety factor is going to the high risk region. So this is really important. You need to identify tree species as sharp as you can. Wind speed. Wind speed, for this calculation, we apply the Euro norm calculation, and the basic wind velocity is defined by the national annex of the standard, and also it depends depending on the geographical location. I changed the wind speed between 20 to 40 meter per second, and the safety factor changed between 50 plus to 190, and the function fits is a second, the power of 2 of the wind speed, so it is quite sensitive. This is coming from the drag equation. Drag equation says the acting force is proportional with the wind speed on the power of 2. And this is just an image from the national annex of the Euro norm. There is a global page, web page, where you can identify the actual basic wind velocity. Most of Italy is 27 meter per second, but there are other regions as well. As you see, the mountainous area is not marked. This is a special area. In those areas, we recommend you to consult with structural engineers and ask what are the basic wind velocity they are using for mountains. In mountains, when your tree is on a hilltop, but it's not in the practice in the Alps, it's much higher, the basic wind velocity, relative to the deep valley, where the wind speed never can be high. Okay, trunk diameter. Again, I saved all the parameters. I changed only the diameter of the trunk and checked the safety factor. You see, when the trunk diameter is 95 centimeter, close to 1 meter, the safety factor is 141. When it's doubled, the diameter almost doubles, 191. The safety factor is becoming 8 times higher. If you multiply 141 by 8, you got 1,100 something. So it's indicating that doubling the diameter results in 8-time increase in the safety factor. And this is the test result. I plotted the safety factor versus trunk diameter, and the equation fit well is a power of 3. This is reflecting again the clear mechanical background. So until now, we can be sure that yes, biomechanics do very well, but it has a very strong limitation. I mean, these calculations were done by the assumption that there is no other building, no trees around. For this reason, the safety factor is, we need to recognize that not taking into account the influence of the surrounding buildings. Let's see this narrow street in Budapest, quite a tall tree, but the tree height is below the height of the building. End of the street, there is another tall building closing the wind. So I got it from the Hungarian arborist, Gábor Ócsváry. He's practicing many years. And for this tree, this is actual data, actual tree in Budapest, the safety factor indicating high risk. 97%. This is really would need to do some action. But he looked around and realized that in this narrow street, big wind never can enter. That's why even this low safety factor, he let the tree grow because his experience. For this reason, I can tell you that the safety factor in a urban situation is always more pessimistic than the real one. I mean, the real one in this case is much higher, and based on the story of this tree, the decision of Gábor Ócsváry was just perfect, and he saved the tree. So yes, we need to look around and modify the risk. Some feature before closing. Yes, just I want to happily report that the number of participants now is over 100, close to 110, and we are really thank you for joining us. And but let me give you some special features of the long nails. In case of Sequoia dendron giganteum, we are using long sensors. The Ludwig sensors is give us more details. The resolution is increased with a moderate price. And just let me show you an article made by Slovakian scientists. They compared the acoustic tomography image, and the names are Radovan Ostrovsky, Marek Kobza, and Jan Gazo. They performed the acoustic tomography with 10 sensors, and they cut the tree and compared the image. Here you see how it is fits. The narrow crack is shown much bigger, but the recognition of the defect is quite accurate. Whenever we have 2 decay spots using 10 sensors, it is impossible to resolve these 2 separate problems. It is unified somehow. And the final statement of this study was the overlapping of the image made by ArborSonic and the cut surface is 96%. Here, 83%. Sometimes the location a little bit shift, and sometimes the size is a little bit shift, but 83% overlapping is, I guess, pretty good using 10 sensors. more sensors, this number would be a little bit higher. This is just another study, a real study from an adventure park. From outside, perfect trunk, but inside, heavy problem. And those platforms made this situation quite risky. And well, some example how to use the caliper. We have two range using the extension arm. The range goes to 2 meters. Let me mention you that we are working on increasing the range of caliper. One idea was using a longer extension arm. We achieved really a big tool, but in practice we found is quite complicated. And that's why we are working on another methodology. I plan to speak the results today, but this development is not 100% complete. That's why next year you will see definitely another solution where we are able to test huge trees. When the setting is wrong, because when you change the range, you need to always set the 0 position by holding the yellow button for long. And these are the mistakes if you forget to do that. If you repair, the test results goes back to this normal. We do this test with students at the Budapest campus of Hungarian University of Agriculture and Life Sciences. Okay, so I guess I just jump to the end, and this is my favorite image. It's made by Tibor Orsi, who already got the diploma, and now he's a practitioner arborist. And this huge platanus tree was tested by him. And here you see the result. He climbed and performed the test, higher elevation. 12 layers were tested. The critical was the crown collar, where they found the biggest decay, but they do not change at all the crown size, but they applied Cobra rope system, 8-ton version, and they secured the branches. And this tree is still a wonderful tree in east part of the country. And at this point, I would like to thank you for your participation.